Okay, so for chapter light, SPM, right? Let's go through a few revisions here. I'm not sure I can finish it, but we try to go through. No means we continue on the 15, right? Okay, now. Reflection light ray diagram for convex mirror. Okay, when you have a convex mirror, remember for any distance of object, image is formed at the back of the mirror or inside mirror. Property of the image, virtual upright diminished. It's a wood, virtual upright diminished. If the light ray is parallel, or when the light ray is parallel, it will be refracted through F, through F. When a light ray is going through the optical center, the light ray will not be refracted, When a light ray moves through the focal point, the light ray will be refracted parallel. See, number 1 and 3 are sama je, arah saja. Okay. Next, for a concave lens, a parallel light ray will be refracted from the focal point. A parallel light ray will be refracted from the focal point. Right? So inside, you have to make it like a dotted line. Dotted line. So a light ray will be refracted from the focal point. Okay. And same like the earlier one, a light ray that goes through optical center will not be refracted, Okay. Next, a light ray towards the focal point will be refracted parallel to the principal axis, like just now, parallel to the principal axis. So these are the 6 light ray diagrams. Okay, these 3 are the common one for convex lens, and these 3 are the common one for concave lenses. Now we look at these 2 are a bit different, okay. The light rays are actually not going through the focal point or even the optical center. So if a light ray travel like this, the light ray will be refracted like this back. Right? If a light ray travel like this, light ray will be refracted back like this actually. These are the 2 refracted light rays for convex and concave lenses. Okay, done with this. Okay, a common question which is very popular everywhere you can see, why a glass prism is a better reflector compared to a plain silver mirror. So nowadays they start asking already, you have a glass prism like in a periscope, okay? When you use a glass prism, why is it a better reflector compared to a plain mirror? Initially those days periscope were using plain mirror, now you started putting a glass prism. So the reason is mirrors produce multiple images due to multiple reflection and the image can be blurred. This is the problem with mirror. The surface of the mirror over the time, if it's not even anymore, this can happen. Next, intensity of brightness in the mirror decreases due to that multiple reflections. So if all the light rays that reach the mirror is parallel, once they are reflected also, if they are parallel, then it's a good thing. But if it is not, you won't get it. And mirror also physically, a silver layer at the back of the mirror, the thickness of the silver layer over the time can decrease. These are the reasons. Okay, so glass prism is a better choice than plain mirror. Next, number 4. The advantages of using a prism in a pair of binoculars. So same reason, we are now using glass prism in a binocular. the distance between the eye lens and the objective lens gets to be reduced. We make it shorter and compact. So the light ray is bent by using total internal reflection. The real image can still be obtained after the light rays pass through the prism. Okay. Next, multiple images are not produced because there's no multiple reflection, because there is no multiple reflection. And there is no loss in brightness because as the light ray pass through the glass prism, all the reflected light rays are not lost, And after the final image is formed, the inverted image after passing through the second glass prism, it becomes upright again. So these are the advantages of fixing two glass prisms in a binocular. Okay. So here, draw a light ray diagram for a glass prism with a critical angle, which I think all of you know already. Okay. Then what is the meaning of critical angle? State the relationship between refractive index and density of a medium. State the relationship between the refractive index and critical angle. Okay, let's discuss this now. Light ray diagram for a glass prism with critical angle. So this is the critical angle, right? As the light ray enter the glass prism, right? The light ray shows that it is refracted with a 90-degree angle on the border between the glass and the air. So it travels here. So critical angle and angle of incident, and the refracted angle is 90, all right? So degree. So this is the light ray that move on the medium of the border. What is the meaning of critical angle? An angle of incident, right? Or incidence where the refracted angle is 90 degree. 90 degree. Next. State the relationship between refractive index and density of a medium. We realize that whenever density of a medium increases, all right, the refractive index increases. So when the density of a medium increases, refractive index increases. Then state the relationship between refractive index and critical angle. The formula shows that refractive index is equal to 1 over sine C. When refractive index equals to 1 over sine C, refractive index equals to 1 over sine C. So whenever the refractive index value increases, the critical angle value will decrease. Any question?
No.
All right, good. Okay, next. Critical angle and angle of incidence when the refracted rays angle is 90.
Sure.
Refracted, yeah.
Next time don't put red color already.
Yeah, Sean told me earlier.
See, wait.
Okay. The refracted ray travels along the two mediums boundary. Just how we saw. Total internal reflection is the total reflection of a beam of light at the boundary of two mediums when the angle of incidence in the optically denser medium exceeds a specific critical angle. All right. Total interreflection occur For total internal reflection to occur, light ray must travel from a denser to a less dense medium, number one. For total internal reflection to occur, the light ray must travel from a denser to a less dense medium, number one. Number two, the angle of incidence now must be more than the critical angle, right? Next, when total internal reflection occur, the boundary between two mediums acts like a perfect plane mirror. Okay, next, we're talking about optical fibers now. Okay, in the design of optical fiber, such as an endoscope, which is used in medicine, optical fiber usage. Okay, so we realize that it undergoes, the light ray inside undergoes total internal reflection. Let's study these optical fibers first. Can you look at optical fibers in the design of optical fibers such as endoscope, which is used in medicine? Okay, see here, this is optical fiber, right? Okay. So what happened here is that when I see this optical fiber, all right, it is made of inner core inside and outer cladding outside, outer cladding. Inner core, outer cladding. Okay, the question here, compare the refractive index of the inner core and outer cladding. The refractive index of the inner core should be bigger than the refractive index of the outer cladding. All right. The reason why, the reason is because we know that, all right, when the refractive index is bigger in the inner core, so the critical angle that is produced in the inner core will be smaller. The light ray easily can undergo total internal reflection. Now, purity of inner core. Purity of inner core must have high purity. Inner core must have high purity so that the light ray that is transmitted here, all these light rays are actually not a common light ray. These are information light rays. Okay, it's a communication light rays. They carry informations, right? It's a coded light ray. So when the system shows high purity, the inner core shows a high purity, the informations are not lost inside there. So they won't experience diffraction or multiple reflections inside there. They just pass through as they were designed to. The light ray, which is actually a communication light ray with coded information, just pass through at high speed, boom, 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 like that. Okay, next. Next, compare the density of the inner core and outer cladding. Density of the inner core must be bigger than the density of the outer cladding, so that the inner core will have a higher or bigger refractive index compared to the outer cladding. Next, finally, strength of the optical fiber. Optical fibers must be strong so that as they are coiled, must be strong. So that as when they are coiled, they won't break. When they are bent and used in a property such like a wire system. See, we fix the broadband in your house everywhere, right? So they should not break easily. They must be strong so that they should not break easily. All right. This is part 1 of chapter light.